All right, welcome to the lecture covering 2.5 Quadratic Equations. I've got Josh in the room with me tonight, so hopefully he will cover any questions that you, the student, might have. So Josh, as usual, feel free to ask any questions that come up during the lecture here. We'll go ahead and get moving forward. Okay, so solving quadratic equations. There are going to be, let's see, 4 or so different methods. Yes, 4 methods for solving quadratic equations that we're going to discuss. So this is just the first of these 4. And I want to point out that when you're solving quadratic equations using factoring, this method is only good when the quadratic expression can be factored. If you cannot factor that expression, you have to go with a different method. However, if the expression is factorable, this is an efficient way of solving quadratic equations. But once again, that's if it is factorable. Factoring means finding an expression that can be multiplied together to give the expression on the one side of the equation. In other words, you have this polynomial that's in a form sometimes that looks just like this, you know, where A, B, and C are values, and you're trying to figure out, okay, what would I have had to multiply together to make that thing? That's where since when you multiply things together, those are called factors. That's why we call this factoring, because you're trying to figure out what you had to multiply together to make that thing. Okay, so one of the first types of problems that we're going to look at is one that is going to be solved by factoring using the AC method. So I grabbed this information here to remind you of how to factor using the AC method. And I'm just going to rattle off these steps real quick. The first step is to find the product A times C. Now, A always goes with the x squared term. B always goes with x, and C is always just the constant tacked on to the end there. So once you find that value, A times C, then you're going to find or think about factors that go together to make A times C, but when you add them together, they make B. And this is the most difficult step of this process. That's kind of the trial and error step of this process. Then you're going to rewrite the BX term using those new factors. I call this step busting the BX. And then you're going to finish this off with factoring by grouping. So once you get that thing factored, you're going to have it looking something like some linear factor times some linear factor, and you may have more than 2 factors, equals 0. You always want to get it to equal 0 because the last step in this process says to use the zero product property to actually solve for x. So these factors look like maybe x minus 3, x plus 4, something like that. The zero product property is extremely simple, but it is very powerful, and it's one of those properties that you will want to put to memory. And what it says is if I'm multiplying things together that equal 0, the only way that could have happened is if one of those factors is actually 0. So what this allows me to do when I have things multiplied together to equal 0, at that point you can say, well, if that's true, then one of these things or both had to equal 0 themselves, then you've just got little linear equations to solve at that point to actually solve for the variable. So I'm going to walk you through these steps through our examples here, but that's just an overview of how you solve with this particular type of factoring method. Okay, so factor and solve the equation x squared plus x minus 6. Okay, so the AC method of solving, of factoring. This is used for factoring something in the form of ax squared plus bx plus c. Your first step is to find a times c. So I'm just going to grab a different colored pen here and point out my a is equal to 1, my b is equal to 1, and my c is negative 6. So a is 1, b is 1, and c is negative 6. So for my first step, I want to find a times c, which in this case is 1 times negative 6, which is negative 6. The second step is to find factors of AC that add to make B. In this case, B is 1. So what I'm looking for here, I'm looking for values that multiply to make negative 6, but add to make 1, which is B. And in this case, so if you think about it, to multiply and make a negative number, you've got to have one positive and one negative number. So in this case, the factors of negative 6 that add to make positive 1 would be positive 3 and negative 2. You're going to use those two factors that you just figured out to complete step 3. And that's rewrite the polynomial, in this case a trinomial, busting the BX. So here's what it looks like. We started out with x squared plus x minus 6 equals 0. I'm not going to write plus x on the inside. I'm actually going to take these two factors that I found and bust this term up. And this is what that looks like. I still have my x squared, but instead of writing plus x, I'm going to write plus 3x minus 2x, and then I have minus 6 equals 0. So if you think about it, positive 3x and negative 2x make positive x. So I haven't changed this thing fundamentally. I've just made it look different. And I've put it into a form that now I can finish off with factor by grouping, which is another method of factoring, but it happens to finish off this particular method. So factor by grouping, your first step there is to split down the center. So let me show you that. I always give myself something to look at. So I literally come in and draw a line, splitting two terms and two terms. Your next step, GCF, that's another method of factoring, just pulling out a greatest common factor. GCF, the first set, so your first two terms. And if I look at those first two terms, I say, okay, what do these two terms have in common as a factor? And they both have an x in them. And then I come back and I divide that factor out of both of those terms and write what I'm left over with. So when I divide x squared by x, I get x, and when I divide 3x by x, I'm left with 3. So this is also known as reverse distribution. So you're pulling it back apart instead of multiplying it together. The third step in grouping is to GCF the second set. And you want to be careful about negative leading terms. You don't want to leave a leading term negative. So if I look at negative 2x and negative 6, they both have a 2 in them. But what I'm going to actually factor out of them is a negative 2, so that my leading term is no longer negative. So when I go back and I divide each of these terms by negative 2, negative 2x divided by negative 2 leaves me with positive x. And negative 6 divided by negative 2 leaves me with positive 3. And I'm still equaling 0. This is still an equation I'm going to have to solve. The last step in factor by grouping is to GCF I call this the big binomial. And I'll show you what I mean by that. Okay, a binomial is a two-termed polynomial. I have one big term here and one big term here. And what those two terms have in common is my GCF. So they each have that factor of x plus 3. So whenever you're working through factor by grouping, you always want to make sure that the same thing shows up on the inside of the parentheses, because that's going to eventually become your GCF. And when you divide that GCF out of those two big terms, you're left with x minus 2. And that equals 0. Your last big step, so I'm coming out of factoring by grouping and back to solving. Well, this isn't actually the factoring method, so let me put a bar there, because that's the factoring method. But to finish solving, you're going to solve using the zero product property. So now we've gotten it in that form of something being multiplied with something else equaling 0. And since that's the case, I can then say, well, at least one of these things had to equal 0. So I set them each equal to 0. And here I'd subtract 3 from both sides and get negative 3. And here I'd add 2 to both sides and get negative 2. This particular quadratic equation has two solutions, negative 3 and 2. They can be written as a set. And that's it. Josh, was that good for you? Did that jog your memory on a bunch of different types of factoring? We actually hit 3 different types of factoring in this one problem. I was worried there for a second. I saw you hit the red X. So we hit the AC method. The AC method is used for AX squared plus BX plus C. We also hit up factor by grouping, and you'll know to use grouping when you have 4 or more terms. So in this case, when you do the AC method, you turn it into a 4-termed polynomial. And then we also reviewed factoring with GCF. So we hit up 3 different methods in this one problem. And Josh is good, so I'm going to move forward. Okay, solve the quadratic equation by factoring. So we've got a trinomial. Let's go ahead and go through the AC method. I'm not going to write the steps this time so that you can start putting them to memory, but I will say them out loud. So I start out with a quadratic equation, x squared plus 8x plus 15 equals 0. My first step is to find a times c. Well, a in this case is understood to be 1. So 1 times 15 is 15. Now I'm looking for the factors of 15 that add to make 8. And that's 5 and 3. I'm going to use those factors to bust the bx term. X squared, I'm not going to write 8x. I'm going to write plus 5x plus 3x plus 15 equals 0. Now I finish it off with factor by grouping. Split it in two. GCF, my first two terms. GCF, my second two terms. And this is important. Always put your sign for the second set. So I'm going to actually take out a positive 3. And you put that there because it comprises the other factor when you GCF the big binomial. I'm left here with x plus 5. My new GCF is x plus 5. And when I divide that out, I'm left over with x plus 3. And that all equals 0. So x plus 5 equals 0. X plus 3 equals 0. Here, x is negative 5. Here, x is negative 3. Now, I'm going to show you something real quick, and this is actually going to be a preview for the next lecture over 5.1 to try to help bridge this gap within our minds between the equations, the quadratic equations, and the quadratic functions. I'm going to show you a graph of this function real quick. So let me take you out to my graphing calculator. Let me make sure my graphing calculator is pulled up. It is. Okay. Okay, so Desmos.com, graphing calculator. Okay, and we were graphing x squared plus 8x plus 15. Okay, the reason I wanted to show you this is we figured out that we had solutions of -5 and -3. And I wanted to point out where this thing crosses the x-axis is at -5 and -3. Those are its x-intercepts. Notice 0 is plugged in for y there because it's an x-intercept. So if we go back to our problem, you'll notice that we would normally see f of x right here, or y. But because it's an equation, we set it equal to 0. That's just like, it's as if we had plugged in 0 for y. So that's why you get the x-intercepts when you solve a quadratic equation. You've always got to have your quadratic equations equal to 0 to solve them, unless you're using the square root property, which we'll talk about in a moment. But if you're using factoring or you're using the quadratic formula, which we'll also talk about, you've got to have them set to 0. So that is how it relates to the graph, because you've in all sense of the problem, you've plugged in 0 for y. So you're getting the x-intercepts out, and they are also considered the solutions to the equation. So the reason they are solutions is because if I took either of these and plugged them back into the original equation, it would make the statement true. So I'll just show you one of them. Negative 3 squared plus 8 times negative 3 plus 15 equals 0. Negative 3 squared is 9. 8 times negative 3 is negative 24 plus 15. Well, 15 and 9 is 24. 24 minus 24 equals 0. 0 equals 0. There's the true statement. And they both work when you do that. That's why they're solutions. You good to go with that, Josh? Okay. Okay, so here's a problem that doesn't look like ax squared plus bx plus c equals 0. We can do this one of two ways. There's another method of factoring that you might recognize with this. So whenever you have a difference of squares, they always factor the same way. In other words, if you can write your polynomial in the form of something squared minus, it's got to be a difference, minus something squared, that thing will always factor as a plus b times a minus b. So in this case, we have x squared minus 25. I can write that as something squared minus something squared. That's x and 5. That means this thing has to factor as x plus 5 times x minus 5. So if you can recognize, and the way you recognize these, two terms and subtraction. If you have two terms and subtraction, see if you can fit it into that mold of something squared minus something squared. So I'll put that up here. Two terms and subtraction. Check to see if it's a difference of squares. Because that's a real quick and easy way to factor that thing. However, you may not recognize that. So I'm going to show you, you can use the AC method with this as well. So the first thing I'm going to do is rewrite this equation. We already know how it's going to factor. But I'm going to rewrite this equation showing all of the terms in ax squared plus bx plus c. So I have x squared. I have 0 x's minus 25 equals 0. Now I've got it in ax squared plus bx plus c form. My a is 1, my b is 0, c is negative 25. I can use the AC method as well. So 1 times negative 25 is negative 25. The factors of negative 25 that add to make 0 are negative 5 and 5. So I rewrite x squared. I'm not going to write 0x. I'm going to write minus 5x plus 5x minus 25 equals 0. Factor by grouping, split them down, GCF, pull an x out. I'm left with an x minus 5. Other side, I'm going to pull a positive 5 out. And I'm left with x minus 5. GCF is x minus 5. Left over is x plus 5, and that's equaling 0. So I have x minus 5 equals 0, x plus 5 equals 0. So here x is 5 or x is negative 5. And I would have gotten the same thing if I had done difference of squares. How is that for you, Josh? All right, cool. So we've hit 4 methods of factoring, and in all honesty, so we hit AC method, GCF, grouping, and difference of squares. If those are all the factoring methods that you can remember, there are others, but if those are all the ones you can remember, then you'll be just fine in this course. Okay, use grouping. Okay, this is the AC method that they're talking about because it finishes off this factor by grouping. Okay, so 4x squared plus 15x plus 9 equals 0. This is a little more complex, but not too much. So I start with multiplying a times c, which is 36. The factors of 36 that add to make 15 are 9, nope, not 9 and 4, that's 13. What else makes 36? 12 and 3. No, I do not work these problems out before I teach. Okay, so I'm going to rewrite 4x squared. I'm not going to write 15x. I'm going to write positive 12x, positive 3x, plus 9 equals 0. Now I'm ready to group. These actually have a 4x in common. And I'm left over with an x and a positive 3. My next side has a positive 3 in common. And I'm left over with x plus 3, and that equals 0. So x plus 3 times 4x plus 3 equals 0. So either x plus 3 equals 0 or 4x plus 3 equals 0. Subtract 3 from both sides, x is negative 3. Subtract 3 from both sides, 4x is negative 3, divide by 4, and x is negative 3/4. So yes, you can have solutions that are not integers. Negative 3 and negative 3/4 are my two solutions here. And that is also where that graph crosses the x-axis. You good with that, Josh? All right, cool deal. Okay, so I put this one on here because this one's got an added step in it. So we're still going to use the AC method, but whenever you are using factoring, and I didn't mention this before and I probably should have, you always want to check for a GCF before you do any other method of factoring. Because if you can pull a GCF out, it's going to make your factoring a lot easier. Well, somewhat easier. So always check for GCF first. In this case, I want to draw that negative off because I don't want my leading term being negative. And each of these terms also has an x in it. So I can go ahead and pull this negative x out, and then I'm left with positive 3x squared plus 5x plus 2. And that equals 0. So I only need to factor, using the AC method, this thing on the inside here. So that's what I'm going to do. So I've got 3 times 2, which is 6. The factors of 6 that add to make 5 are 3 and 2. So this negative x out front, it's just going to come down, and it remains a factor, but I'm going to give myself lots of room to finish off the factoring of that trinomial factor there. Okay, so I start out with 3x squared plus 5x plus 2. I don't write 5x, I write plus 3x plus 2x plus 2. And I split it. I'm going to take a 3x out here, and I'm left with x plus 1. I'm going to take a positive 2 out of the other side, and I'm left with x plus 1. So this thing factors as x plus 1 times 3x plus 2. So let me show you what you have now. You have a factor of negative x. You have a factor of x plus 1. And you have a factor of 3x plus 2. All those things had to be multiplied together to make that polynomial you began with. So even though you've got 3 factors, you still use the zero product property. It doesn't matter how many things you're multiplying together to make 0. One of them had to be 0, at least. So negative x equals 0, x plus 1 equals 0, and 3x plus 2 equals 0. X is 0 here when I divide both sides by negative 1. Here I'm going to subtract 1 and get x is negative 1. I'm going to subtract 2 first, and then I'm going to divide by 3, and I get x is negative 2/3. Let's take a look at this one on the graph. Let me write it down, or I will surely forget what the equation is. Let me grab a pen. All right. So we have negative 3x cubed minus 5x squared minus 2x. Okay, let's go check this graph out real quick. Oh, let me write down what we ended up with as solutions. We ended up with 0, negative 1, and negative 2/3. All right. So watch this. That's cool. Thanks, Josh. Okay, so we have negative 3x cubed minus 5x squared minus 2x. All right, so I'm going to zoom in right around where we cross the x-axis, and I'll just remind you, we ended up having a solution of 0, an x value of 0. We had negative 2/3, which is negative 0.666, and so on, and we had a negative 1. So even though there were 3 factors, that's still exactly where that graph crosses the x-axis. Pretty cool, huh? At least in my nerdy mathematical world, that's cool. Thank you, Josh. Okay, so here's our next method of solving quadratic equations. This method is only good, let me write this at the top, only good when there's no bx term. Just x squared and just a value. No bx term, or you can't use it. Oh, and it says it here in your book. No x term. Okay, so when you are given this situation, what you want to do is first isolate your squared term on one side of the equal sign. Then to undo x being squared, you're going to take the square root of both sides, because taking the square root of something squared undoes it. It's its inverse, and you're just left with x. And then you're going to simplify the other side. Don't forget, you've got to take into consideration the positive and the negative values. And here's what I mean. If I have x squared equals 9, this is saying, what can I multiply by itself to make 9? Well, I can multiply 3 and negative 3. by themselves. Like -3 times -3 is positive 9. 3 times 3 is 9. So you have to take into consideration the positive and the negative. And you have to recall how to simplify a square root, perhaps. With this particular one right here, you do. So we start off with x squared equals 8. My squared term is already isolated. I don't have to do anything to isolate it. So I'm ready to take the square root of both sides. When I take the square root of x squared, I'm left with x. And on the right-hand side, I have to take into consideration this could have been the positive or the negative square root of 8. I'm not quite done, though, because 8 has a perfect square factor in it. I can break that down into the square root of 4 times the square root of 2. Oops, I just wrote 4 again. Because 2 times 4 is 8. I can come back and actually take the square root of 4, which is 2. So my final answer here, or solution, is positive and negative 2 square root 2. So I've got two solutions there. If I were going to write them in set form, I'd have the negative 2 square root 2 and positive 2 square root 2 as my solution. You all right with that method of solving, Josh? Is this making sense so far? Okay. This next one, we're going to use the same method, but we actually have to isolate the square before we can take the square root of both sides. So we start with 4x squared plus 1 equals 7. And then I am going to subtract 1 off of both sides. And that leaves me with 4x squared equals 6. I'm not done isolating yet. I need to divide that 4 off of both sides. And I get x squared is equal to 6/4, but that's the same thing as 3/2. Now, on some of the homework in the last test, I had a lot of people trying to change their simplified improper fractions into mixed numbers. Don't do that. Just leave it as a simplified improper fraction. The only time it's beneficial to change it to a mixed number is if you're going to go graph it like as a point, because it's easier to think about graphing an x value of 1 1/2 instead of 3/2, or if it's a word problem where it makes sense to turn it into a mixed number. Other than that, just leave it as an improper fraction. It's much easier to work with like that. Now that I'm isolated with my x squared, I can now take the square root of both sides. Square root of x squared is just x, and I have to take into consideration this could have been the positive or the negative square root of 3/2. Now, I have seen in WebAssign, you know, this is the first semester I'm using WebAssign, that they will accept an answer like this. But technically speaking, you should not leave your answer like this, and it may come to a point the further we get into the material where WebAssign quits taking this type of answer, and here's why. You can actually use your quotient rule of roots and split your fraction with the square root of 3 over the square root of 2. And we learned in the last lesson on complex numbers, or remembered rather, that you can't leave a root in the denominator. So you have to rationalize the denominator. And to do that, I multiply it by whatever's going to give me an integer. So I'm going to square that square root underneath to get rid of the square root. All right, so I get x is equal to positive or negative. Well, square root of 3 times the square root of 2 is the square root of 6. The square root of 2 times the square root of 2 is the square root of 4, but the square root of 4 is just 2. So you're squaring that square root in the denominator. There's your final answer. square root of 6 over 2. So x is equal to the negative square root of 6 over 2 and the positive square root of 6 over 2. And like I said, I'm not sure how much longer they're going to take you leaving your answer in that form right there. I'm sorry, Josh, were you good with everything? Okay. All right, same thing. We're going to use the square root property. This one looks a little different. You see your squared unit is actually a linear factor itself. So we start out with 3 times x minus 4 squared equals 15. We still want to isolate that squared term. So I'm going to divide both sides by 3. And that gives me x minus 4 squared is equal to 5. Now I've got my squared term, well, factor, isolated. So I can take the square root of both sides now. Taking the square root of something squared leaves me with just that thing, and then on the other side I have to take into consideration the positive and the negative square root of 5. But I haven't isolated x yet. I need to add 4 to both sides to get it by itself. X equal to 4 plus or minus the square root of 5. So there are 2 solutions there. We have 4 plus the square root of 5, 4 minus the square root of 5. You good with that? Okay. Okay, so this is probably the most confusing method of solving quadratic equations. Once you get the steps down and get the hang of it, it's not that bad, but when you first look at it, it can be confusing. This particular method is not going to be used very much at all in this course, but it will be very helpful for you once you get into pre-calculus and calculus to know how to complete the square. So I decided to go ahead and teach it. Okay, so completing the square. Not all quadratic equations can be factored or solved using the square root property. In these cases, we may have to go to a method called completing the square. Using this method, what we do is we add or subtract terms that are going to create a perfect square trinomial that then we can use the square root property to solve. And I found a list on Google Images of the actual steps. And since I did not include this in your notes, what I did was made a picture file of these steps by themselves, and I uploaded it into D2L. So if you want these steps, you can, there's a picture of them in D2L in that module folder. To complete the square, the leading coefficient must be equal to 1. So if it's not, then you need to divide off whatever factor is not 1 through the whole equation. In this case, my A is equal to 1. So I'm okay to go ahead and start completing the square here. And here's how we do it. We start with x squared minus 3x minus 5 equals 0. Okay, look, your first step says don't forget your A's got to be 1. So let's just say that this had been a 2. If it were a 2, I'd have to divide the entire equation by 2, creating fractions on the BX term and the C term. Okay, so your next step is to isolate the x squared and bx on one side. So I'm going to add 5 to both sides here. It's a little different in the other methods. You don't have to have it equal to 0. As a matter of fact, you don't want it equal to 0 yet. X squared minus 3x equals 5. And yes, I left a space there on purpose. So your next step is to take half of the coefficient b on the bx term. So off to the side, b is equal to -3, and half of b is equal to -3 halves. So you just half your b, your bx coefficient. So, and then you square that and add it to both sides. So I'm going to add -3 halves squared. I can't just add it to one side for it to remain an equation, so I have to add it to both sides. Okay, so now I have x squared minus 3x. Okay, when you have a fraction squared, you square the numerator and square the denominator. So that is plus 9/4. It becomes positive because that negative gets squared as well. And so on this side, I have 5 plus 9/4 as well. And then you have a perfect square trinomial that has been built on the left-hand side. Because I didn't go through that particular method of factoring, off to the side here, I'm going to show you, you can use the AC method now to factor the, well, yeah, I should probably show you what a perfect square trinomial is. Let me get a new page in here. So let's say we have x plus 3 squared. A perfect square trinomial is a trinomial that came from squaring a linear factor, so multiplying it by itself, like that. And when we do all of our distribution here, I get x squared plus 3x plus 3x plus 9. So that's x squared plus 6x plus 9. Now let's look at this in very general terms so we can see the pattern that emerges. So let's use a's and b's. A plus b squared. That's a plus b times a plus b. So that's a squared plus ab plus ab plus b squared. So the pattern that emerges is you have a squared plus 2 times a times b plus b squared. So if you can figure out what was squared to make that first term and what was squared to make that last term, you can figure out where that trinomial came from, what it factors as. And the only difference in having minus, let's say you have a minus b squared, that's a minus b times a minus b. Your middle term's negative. Everything else is the same. So you have a squared. A times negative b is negative ab. Negative b times a is negative ab. And negative b times negative b is positive b squared. So this, you have a negative 2ab plus b squared. Okay, so these are perfect square trinomial forms. Let me actually grab a picture of these and we'll take them back and paste them here so we can have them to look at. Whoops. The marvels of modern technology right there. All right, so basically, you know that your middle term is negative here. So it had to be an a minus b times an a minus b. And I'm looking at the left-hand side. I know that my a had to be x, because x times x is x squared. So I can go ahead and put x minus and then squared. And 5 plus 9, we'll worry about this fraction-y math in a second. I'll do 5 over 1 plus 9 over 4, and we'll get ready to combine those fractions on the other side here in a moment. Well, now all I need to do is figure out, well, what the heck did I have to square to get 9/4? Well, you already know what you had to square to get 9/4. The negative doesn't come into effect because you've already got the minus there. So this thing factors on that side as x minus 3 halves squared. That's what completing the square is. The reason it's called completing the square is because you had to complete it by figuring out what half of b was, squaring that, and adding it back in. Have I lost you, Josh, or are you okay so far? Okay, cool. So now, if you recognize it, what I've done is I've turned that left-hand side into a squared factor that once I combine the right-hand side, I can just take the square root of both sides. So it can be a little tricky, but once you practice it a couple times, it's really not that bad. All right, so on the right-hand side, I've got fractions that I'm trying to add, and they don't have a common denominator. So I need to come over here and multiply by my clever form of 1 that gives me that denominator I'm trying to get to. So on this side, I've got x minus 3 halves squared, and that equals 20/4 plus 9/4. So x minus 3 halves squared equals 29/4. Now I've got my squared term isolated. I've got my fraction-y math done, so I'm ready to take the square root of both sides. The square root of x minus 3 halves squared is just x minus 3 halves. And the square root of 29/4, well, that's the same thing as the square root of 29 over the square root of 4. So this is the positive or negative square root of 29 over 2, because the square root of 4 is 2. And now, when I add 3 halves to both sides to isolate my x value, I've already got halves on that other root fraction there. So I don't have to get a common denominator. I get x is equal to 3 halves plus or minus the square root of 29 over 2. You can either write it like that, or since you have a common denominator, you can also say this is 3 plus or minus the square root of 29 over 2 by combining your numerators over your common denominator. Have I blown your mind, Josh, or are you all right? Okay. Let's hold off completing another square. I put it in here to have another one to do, but we've still got a few slides to get through, and we're coming up on 7 o'clock. This one's ready, though, to complete the square. You don't even have to subtract over. You just need to take half of b, add it back on, and do your thing. Okay, so here is some good news. If you forget everything that I've just taught you, and I'm being serious when I say this. If you forget every method I've just taught you, the quadratic formula always works. Big, cheesy, smiley face on that. So say you get to the test and you're on this part of the test and you just blank out. If you can just remember the quadratic formula, you can always solve a quadratic equation. No matter if it's factors or not, no matter if it's got imaginary solutions, this is your ticket. The quadratic formula is used to solve quadratics in the form of ax squared plus bx plus c equals 0. I've already shown you if all of those pieces don't show up, put in 0 for it. So maybe you have 0 x's, or maybe you have a plus 0 on the end. But this always works. And the quadratic formula is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And it says x equals, so when you're solving, you're actually solving this. You don't have to do anything else but put those values in and simplify to solve. Okay, so I'm already in standard form, ax squared plus bx plus c. Here a is 1, b is 1, and c is 2. And I'll just write down the quadratic formula on this page so you have it. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so I'm ready to go. X is equal to the opposite of b plus or minus the square root. Now when you plug in here, especially if it's a negative value, you always want to plug it in parentheses. B squared minus 4 times A times C all over 2A. Okay, I'm just going to continue. Plus or minus the square root of 1 minus 8 over 2. X is equal to negative 1 plus or minus the square root of negative 7 over 2. X is equal to negative 1 plus or minus, this is the square root of negative 1 times the square root of 7. We learned that last lecture. X is equal to negative 1 plus or minus I square root 7 over 2. We have two imaginary solutions. Let me show you what this means graphically. X squared plus x plus 2. All right, x squared plus x plus 2. Okay, I've got to zoom out. Notice, this thing does not cross the x-axis. It's floating above. That's why you have imaginary solutions, because there are no x-intercepts for this particular parabola. Does that make sense, Josh? Okay.
Hey, I'm in the library and they're about to close, so I'm going to have to log off on you.
All right. All right. Thanks for coming, Josh. I appreciate it. Have a good evening,
All right,
man.
You too.
Okay. We're going to continue forward. Joshless, though. Okay. Solve using the quadratic formula. Once again, x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. X is equal to, let me note a, b, and c first so nobody gets confused. A is 9, B is 3, C is -2. A always goes with x squared, B always goes with x, and C is always the constant. So the opposite of B, plus or minus the square root of B squared minus 4AC all over 2A. All right. -3 plus or minus the square root of 9 plus, let's see, 36 times 2 is 72 over 18. X is equal to -3 plus or minus the square root of 81 over 18. X is equal to -3 plus or minus, well, the square root of 81 is 9 over 18. So we can actually figure out our two answers here. We've got a plus and a minus. We have -3 plus 9 over 18 and -3 minus 9 over 18. -3 plus 9 is 6 over 18, which simplifies to 1/3. -3 minus 9 is -12 18. 6 goes into both of those, so that's -2/3. So x is equal to -2/3 and 1/3. Okay, this is the last thing with this, the discriminant. Okay, so the quadratic formula not only generates the solutions, but it also tells you what sort of solutions you should expect when we consider what we call the discriminant. The discriminant is the part of the quadratic formula that's underneath the radical, b squared minus 4ac. And it tells you how many and what type of solutions you should expect. Because we thought, you know, there are different ways that thing can cross or not cross the x-axis. So if your discriminant, b squared minus 4ac, is equal to 0, you're going to have one rational solution. If it's greater than 0, you're going to have two rational solutions. If it's, and a perfect square, you're going to have two rational solutions. If it's greater than 0 and not a perfect square, you're going to have two irrational solutions. And if it's less than 0, you're going to have two complex or imaginary solutions. Okay, so let's take a look at this last problem. And it's just finding the discriminant for each of these. So for A, we have x squared plus 4x plus 4. And there is an understood A of 1. So my discriminant, all I have to do is the b squared minus 4ac part, the part that's underneath the radical, to know what to expect. So that is 4 squared minus 4 times 1 times 4 is 16 minus 16, which is 0. I should expect one rational solution. And real quick, if I go graph this, I'll show you it touches the x-axis right at the vertex. X squared plus 4x plus 4, but one solution right there at -2. So the discriminant doesn't tell you what the solution is. It just tells you how many and what type to expect. So when you get 0, it's one integer solution. All right, let's do it for the others. B, we have 8x squared plus 14x plus 3 equals 0. B squared minus 4ac is 14 squared minus 4 times 8 times 3. Okay, I gotta grab my calculator. 14 squared is 196, and 4 times 8 times 3, that is minus 96, which gives me a discriminant of 100. Think about the fact that that's sitting under the square root, and that is a perfect square. So when you take that perfect square, you're going to end up with just 10. Or when you take the root of that perfect square. So you're going to add 10 one time when you go through, and you're going to subtract it. So when you have a discriminant that's greater than 0 and it's a perfect square, you're going to have two rational solutions. By the way, when you get 0, you've got one rational solution. Okay? For C, 3x squared minus 5x minus 2 equals 0. B squared minus 4ac, negative 5 squared minus 4 times 3 times negative 2, which is 25. Let's see, 12 times 2 plus 24, which is 49. Oh, we got another two rational solutions. Did I do that right? Yeah, I guess I did. I thought that they would give us one of each, but I got tricked. So two rational solutions because 49 is a perfect square. And D, 3x squared minus 10x plus 15 equals 0. B squared minus 4ac is equal to negative 10 squared minus 4 times 3 times 15. That's 100. Let's see, 15 times 4 is 60 times 3 is 90, so minus 90. That leaves me with 10. 10 is not a perfect square, but it is greater than 0, so it's not an imaginary solution or complex solutions. This is going to be two irrational solutions. All right, that's all I have for you for 5.1. I hope this was helpful.